Okay. So good morning and happy Friday. Thank you for your exam two submissions. I saw them last night. So today, um, the the let's see what I was going to say. Yes. Today, we're going to finish up where we left off, excuse me, on Monday, with the balance of our discussion on max likelihood estimation. And then with the balance of the time, we will start an intro to the material concerning machine learning. And so I'm a little bit worn out. As you know, I'm chairing the search committee for the teaching track position. And part of that interview process is the faculty and staff take the candidate out to dinner. And since I'm the chair, I was the host and sort of had to stay till it was all over and ended up getting back home fairly late for me. So hopefully I'll remember everything I have to say, but moral of the story is especially if you're interviewing and you're going for a job that's like a consulting job, nonprofit job, any sort of job, like academic job, where you're going to interface a lot with people. If part of that interview includes being taken out to dinner, remember that's not social, that's part of your interview. And what they're trying to do is see or answer the question, can I work with this person? How does this person socialize? So it really is not technically social. It is part of your interview process. So if you ever are interviewing, graduating, interviewing for a job, if part of that involves dinner with the folks with whom you'd be working, always remember it's still part of the interview. All right. So before we begin, the usual administrative bits, there's new reading. It's an excerpt from a book called Learning from Data, and that's going to be in support of the material on machine learning. It's written by Dr. Yasser Abu Mustafa, who is a full professor of computer science at Caltech, California Institute of Technology. And he is both well regarded as a researcher, a pioneering researcher in the field, but also has won very many teaching awards. The book is very well written. And so that's posted on the Canvas site, linked as book:"Learning from Data, Chapter 1. And that's in support of the material for the intro on machine learning that we'll cover with the balance of today, and then let the rest spill over into Monday. And so after today, there's only 2 weeks and one day left in this semester. And after that, you don't ever have to hear me talk about this stuff again. Maybe that's good news, maybe that's bad news. But I know one or two of you has registered for my stochastic computing course in the fall of 2023. Okay. Any questions? No? All right. And so I've modified the slides a little bit from what I posted. Again, my Kaizen continuous improvement. I thought it would be useful to give you some visuals, in particular for optimization, about one way to think of functions that one might enterprise to minimize or maximize. Okay. So where we last left off for max likelihood estimation, we were framing it in an example, Mr. Bond's coffee shop. And we said we take our data and we postulated that the Poisson distribution was the best distribution to describe it. Yes, you have events in time in standard windows of observation, delta t, and it didn't matter what that delta t was. We're just using 15 minutes for each time window. Just for this example, you can set it to whatever you choose for your modeling. And so we built the so-called likelihood function, and that likelihood function is an evaluation of the mass function or the density function on each one of your observations. And so, of course, if you had 1,000 observations, there'd be 1,000 evaluations. And when we do this, we put them together, and what we're enterprising to do with that is come up with a single function that describes the probability for that data that you're given. And we're going to use this function to find the notional best value of lambda. And our idea of best value of lambda, which is a free parameter, it's the only variable in this expression is that lambda that maximizes this so-called joint likelihood function. Okay, to jar your memory. Any questions? No? No questions? All right. And so mathematically, we would write it as a super product. So it's the product for I goes from 1 to n, where n is the number of samples, IID independent and identically distributed samples from your modeling distribution. And we're just going to multiply each one of these evaluations, P of xi, as we saw on the previous page more graphically. And so we said that this is a messy form, this product, and to clean up this function, make it easier to deal with, we're going to apply transformations to it, a special group of transformations, so-called monotonic transformations. And we said those monotonic transformations are order preserving in terms of the values that we're going to try, values of lambda, to solve for this so-called joint or product likelihood function. Does that make sense? Any questions? Jar your memory from Monday? Monday seems like such a long time ago. All right. So then we computed these monotonic transformations, and we took the natural log. Log is a monotonic transformation, monotonic function. And this turned our product into a sum. And then we evaluated this log on the probability mass function. And we got the following expression, our sum, for I goes from 1 to n, down below, of minus lambda plus xi ln lambda minus ln of xi factorial. And so that's just the natural log of the mass function for the Poisson distribution. Okay, so then now our problem changed from finding the lambda, our free parameter, that maximized this joint product likelihood function, and it turns into finding the lambda that maximizes this so-called log likelihood function. And so because these were monotonic transformations we applied, the version of lambda or the value of lambda that maximizes this expression is also going to be the same lambda that maximizes the original product likelihood that we had on the previous slide. All right, any questions? Does that make sense? Yeah? All right. So this is going to be our function, and we're going to find the maximum of this function in any sort of optimization problem. It doesn't matter if you minimize or maximize. We could certainly turn this maximization problem into a minimization problem just by negating everything, right? Multiplying by a scalar is a monotonic transformation. And so I'm just going to talk generally maximize or minimize. But for this particular function, as we've presented it, we're going to try to maximize that function. And so it is a function of lambda. Recall, when we compute the product likelihood and then transform it, each one of these xi's, those are measurements. So they're values, like 37 degrees, 29 degrees. And as values, or in this case, 5 customers or 3 customers arrived at the coffee shop. And as values, they're constants. And so the only variable in this expression is going to be lambda. And so you can think of this log likelihood, this transformed product likelihood function, as a function of the free variables. And because the only variable that we have in this expression is the lambda parameter from the original Poisson mass function, we're going to call this a function of lambda. If we did similarly with the gamma distribution, this is going to be a function of 2 things. It's going to be a function of alpha and of lambda, because that mass function for the gamma distribution, the free variables are the alpha number of steps in the multi-stage execution model and the time parameter lambda. Does that make sense? Any questions? No? All right. And so this is our function that we're going to maximize. But more generally, you can have more than one free variable, and therefore your log likelihood function is going to be a function of those free variables. And for the distributions, those free variables that define this product log likelihood function are going to be the parameters of the model distribution that you've selected. Okay. Any questions? No? No? All right. So we're enterprising to find the minimum or maximum of a function. And so oftentimes in optimization, we think of a function as represented as the height of some very bumpy terrain. And here along the x-axis, that's the front edge along the bottom here, and the y-axis, instead of x and y, we're just going to call it the first axis and the second axis. And each position along that planar surface is going to be an instantiation, a value of the first parameter or variable and the second parameter or variable. And we're going to consider in this landscape, the elevation is going to be the value of the function. Now, I've drawn it to be always positive, but it doesn't always have to be positive. And when we think about optimization, the finding of a minimum or maximum of a function, it's often imagined as a terrain, like you see here. And this is a so-called two-dimensional function. Yes, it's drawn in 3 dimensions, but the free variables are in 2 dimensions, these parameter axes. Does that make sense? Any questions? Yeah. And so when you're trying to find the minimum, there are many different ways you can perform optimization. You could get a graduate degree, make a life study at the PhD level just with optimization. It's used in business and economics and all sorts of disciplines, including computer science. And so when you're finding this minimum, it's thought of as placing a marble, if you will, on this terrain. And then you shake the terrain, this marble starts to roll, and it's going to roll in some direction. And the goal then is to get this marble to move in a way that it comes to rest at the lowest point or the valleys, if you will, of this function, right, of this terrain. And so there are lots and lots of ways you can do it. But there are a few practical problems that occur in most real functions, and a probability, as we know, is nothing more than a function. And if you have a very complex probabilistic model, it's more often than not your function, your probability, your model is going to be a very complex terrain in terms of the values that it can take on. And so the difficulty in finding your minimum values has to do with what are called local minima. And these local minima are these little pits, if you will, that occur along the way in your terrain. Now, certainly you're going to have minima dotting this landscape. And so how you're going to move this marble or cause it to move, there are many techniques for doing that. And so among these minima is some minimum that is the smallest or the lowest in terms of the elevation or the functional value among all of the little pits along the terrain that can occur. Does that make sense? Any question? And so one popular class of finding of methods for finding these minima are randomized methods. And so the idea then is you change the value or the positions of the marble, and then you let it roll downhill, right? And those methods that say find the minima by letting this marble roll downhill are so-called local hill climbing approaches. They take what's called the gradient or the local slope of the terrain in some patch around it, and depending on the direction of the steepest slope, they let the marble roll for some number of time steps or iterations. But certainly that approach is sensitive to these local minima, because if this marble, for example, in this landscape, comes down to this first local minima, traverses a path, it's going to get stuck. So what do you do? Okay. Well, there are methods that say if your local hill climbing approach, your local gradient search, gets caught in a local minima, you jiggle it a little bit, insert some so-called Brownian motion. You randomly select a perturbation that pushes the marble in some direction, and the hope is you'll push this marble in some direction when it gets stuck in a local minimum. You'll push it in a way that it's potentially going to roll out of that local minimum. Does that make sense? But of course, there are lots of practical considerations. How much do you push it? And are you going to push it the same amount depending on how it gets stuck? Now, there are other versions of search, randomized search, that are completely random. And with this, you select a value for placing your marble somewhere in the landscape. Let me select, let's see, this is like red. Let me select this dark red. You randomly initialize the location of the marble. You record its elevation. So you record this elevation. And then you randomly select another location for the marble. You record that elevation. And then you randomly set some number n of many locations. Each time you're measuring your function value, and then you keep whichever one is the smallest. Now, when you do that, you can think of this randomized technique as being quote unquote global in its scope. Because it's random, if you select these locations for which to evaluate the height of your terrain where the marble sits, when you select these randomized locations, you have full reach over all of the places where this terrain or this function is defined. Now, this idea of random selection, you can almost think of it as probing, right? So if you were kind of walking around, you close your eyes, you kind of, tap your foot around, and you're kind of feeling around you for what that terrain is. So you're probing your terrain in a global scope, and you're doing that randomly to try to find the minimum, the lowest pits, so to speak, of this terrain map, the function we're trying to find the minimum for. Now, of course, that has benefit because you're going to find eventually this global minimum, but it can be very slow to converge, to reach its final value, because there might be a large number of locations that you could conceivably try. Now, there are some mixed methods that try to balance between this local hill climbing and this global search. And those methods will take your landscape, divide it up into regular cells, and then jump in regular increments globally. And then once it finds the smallest of those global jumps, it'll pick the smallest one or the one that's lowest in the relief map and then engage in hill climbing. And there are a lot of other methods that switch regimes between this global search and this local search. But nonetheless, in computer science and in machine learning and model fitting in general, this idea of randomized search is really, really important because min finding and max finding is the key for methods such as max likelihood estimation. Does that make sense? Any questions? No? All right. And so I forgot why I highlighted that. I can't remember. Let's continue on with where we left off with a little bit of definition. In optimization, you have something called your objective function. And your objective function is that functional form that describes a goal that you're trying to reach. And so this objective function, in our case, is the transformed product likelihood function, namely the log likelihood function, and converting through monotonic transformation from a product to a sum is just a mathematical convenience because it's a lot easier to perform minimization when you have sums of terms versus products of terms. And so the idea then is how to find what are called feasible solutions, all of those different positions, if you will, on the relief map that are closer to this global minimum. Does that make sense? Okay. And so this is going to be our objective function. And more formally, if you go off and read the literature, you'll see an expression like this. Argmax says the argument or value of lambda that minimizes this function, and that function between the open and closed curly brace, that's the objective function. And we're going to call that lambda hat, and that's going to be our estimator that we're going to use as the reasonable replacement for the original Poisson IID model. Does that make sense? Any questions? Now, of course, in an optimization class, you would study various families of functions, looking at their properties. Are they differentiable? Are they piecewise differentiable? Are they smooth? Are they bumpy? How bumpy are they? And can you approximate the function? And all sorts of stuff like that. But we're going to just assume that it's differentiable, which it is, because probabilities are differentiable. And we're not going to cover out some or a lot of those optimization questions. But please know that for many of the learning APIs, when you get into the more complex ones, it affords you the ability to choose the method by which you find the minimum or maximum of these functions. And those methods, how you search through all of those locations on the relief map, can greatly impact or detract from the quality of the resulting solution you're enterprising to find. Okay? So just to make you aware of that. Okay, so this idea of best describes the data, and I'm a John F. Kennedy fan, so of course I had to find a video for something. And I can't release the pen. There we go. Okay, that was in I think it was 68. It was 68 or 65, something like that. Oh no, today's working out that way. I just accidentally killed the share. All right, there went my punchline. Let me re-maximize. And let me go to that version of slideshow. And so for the good of your models, ask not what you can do, what Lambda can do for you, ask what you can do to find your Lambda. And so I'd like you, then, the goal is to find the Lambda that maximizes this expression. And because, as I said before, these are monotonic transformations, the value of Lambda that maximizes the sum form is also going to be the same Lambda that maximizes the product form. Let me hide the meeting controls. Okay. So how do you find the maximum of a function? As we talked about with our stochastic methods, you can try a lot of things. So let's look at some of these considerations. You could do a sequential search. Okay. Well, if we have our function, we know the parameters, and these parameters have values over which they are defined. And so imagine then you have your function, and this particular function is our objective function, and that function is very bumpy. It's a very hilly terrain with many pits and valleys and peaks. And so we find our low value and our high value that our parameter, our free variable lambda can take on. And then we grid it or we partition it into deltas, standard steps, and then we try our values. And so we'll take the first value or the first delta step among our values over which that variable is defined. We evaluate our function. Okay. We do it again. Okay. Second one. At some point, we're going to be somewhere near, and I say somewhere near, the maximum value. I'll call that xm. We evaluate our function, and each time you're remembering the height of the relief map or the value of that function for which you're trying to find the maximum. And so you keep going, keep going, keep going until you reach the boundary, upper boundary for your range of values your variable can take on. And then you just remember your maximum. Okay, that's fairly straightforward. But then the question then is how wide is this increment between, say, x1 and x2, our delta? Now, of course, if it's very, very narrow, you're going to get really close to finding this maximum point or this maximizing point xm. But the problem is if these deltas or these steps between each increment, x1 to x2 or xi to xi plus 1, if that step is too small, it's going to take you a really long time. So there's this classic trade-off between granularity and computational feasibility, right? You can't get around that. So you could say, all right, well, there's a problem. It can take too long. And then to make it work in practice, you have to have these steps between adjacent points that you're probing. And you're going to make it feasible if these steps are larger, but you're not guaranteed to find the maximum. And the reason you're not guaranteed to find this maximum, excuse me, is because if your delta is too large, you might jump past this maximum and you won't get good optimization results. Does that make sense? Any questions? No? All right. So then let's take a look at random search. Again, you find the boundaries where your function is defined. And again, it's a hilly landscape with lots of pits and valleys and peaks and trenches. So you randomly select a value in your span, okay, evaluate your function, randomly select another one, evaluate your function, keep randomly selecting. Now, of course, there's a problem with this. You don't know how many iterations over which to make your random or place your random probes. You can have repetition because if it's uniform at random, that's kind of required if you want global reach in terms of your probe points on the terrain. And you can also take a very long time in order to get very good coverage of different regions or so-called basins of attraction in this landscape. And so randomization can work in some cases, but you really, with this randomization, want to trade off between the global reach where you place your probes and then switch to a regime of local hill climbing once you find something that's relatively low among all the global probe points on the landscape. Does that make sense? Any questions? No? Yes. Yes. Yeah, well, yes, you can. Maximum, minimum, it doesn't matter. Through negation, you can turn it to a minimization. Mostly in the literature, they always talk about it as local minima, but local maxima is the same thing. You can have a local, peak in your landscape. Yeah. If you're making it a maximization problem. But generally, they treat them the same because through monotonic transformation negation, you can turn a maximization to a minimization. Okay. Any other questions? No? So let's take a look at something else. And for this, we're going to draw a tangent line on our function. And a tangent line touches the function at one point, and its slope represents the slope of the function at that particular point over the values which is defined. So we take our tangent line, and let's just kind of move that tangent line around. And of course, at this point, we notice something happens with the slope of our tangent line. And let's take a closer look at it. The slope is 0 at the maximum point or the turning point of the function. Now, when we're going up to that maximum, that turning point, it's a positive slope, and then it becomes a negative slope. So somewhere in between, it had to reach a slope of 0. And so you can use calculus by setting the derivative to 0 and solving in order to find the minimum, the maximum. But this isn't really the maximum, right? It'll return back local maximum, if you want to call it that, a set of maxima candidates. And then you would turn to the second derivative to see if it's curvature positive or curvature negative in order to know whether it's the maximum, the maximum or the minimum. But nonetheless, we're not going to talk about the second derivative test. We're only going to talk about the first derivative test because we want to make the assumption in this simple case that imagine the function just has one maximum. Okay. Any questions? No? Now, of course, this assumes, which probabilities are, that these functions are smooth, meaning differentiable. There are no disjoint changes, no discontinuities in it. So the derivative is defined anywhere over which the function is defined. So we take the derivative of our function and we set it equal to 0 and solve for the unknown, x in this case, but in the case of our product likelihood function that we've transformed, it would be solving for that derivative with respect to lambda because lambda is our variable for the function for our Poisson model. Does that make sense? Any questions? No? So let's take a look at the Poisson MLE. We're going to take the derivative of our objective function, set it equal to 0, and we're going to solve for lambda. Okay, so we had the joint likelihood function, and we converted that through our monotonic transformations to a sum. So we take the derivative, in this case, with respect to lambda, in order to solve for the value of lambda, where this thing reaches the turning point, which is the maximum. And so in a model that has more than one parameter, you're going to have to do this derivative with respect to each one of the parameters. So in the case of a gamma likelihood function, you're going to take the derivative with respect to alpha and set it to 0 and solve for alpha. And then you're going to have to take the derivative with respect to lambda, set it equal to 0 and solve for lambda. Now it works because if you take the derivative with respect to a particular variable, if you have a term in that expression that does not involve that variable, it's effectively a constant, and the derivative of that constant is always 0. Okay, to jar your memory about a little bit of calculus. Any questions? No? And so the derivative of the sum is the sum of the derivative. And you can think of it as distributing this derivative function through the summation. And so now we have the sum, I goes from 1 to n, of dd lambda of this term minus lambda plus xi ln lambda minus ln of xi factorial. Now, if we take a look at this, well, we have 3 terms here. And the first term, that involves lambda to the 1 power, all right? The second term here, that involves a function of lambda. But this third term here doesn't involve lambda anywhere. For all intents and purposes, it is a constant under this derivative with respect to lambda. So this third term is going to go to 0. Moreover, the natural log, the derivative of natural log of a variable is just 1 upon that variable. So let's see what this next step brings us. And so lambda to the 1 power, the derivative of some variable to the 1 power is just 1. So we have minus 1 for our first term, and that's for the derivative with respect to lambda of minus lambda. Okay. And then we have 1 upon lambda. That's the derivative with respect to lambda of this ln lambda part. We're multiplying by x. Now remember, xi, that's each one of the measurements, so that's a constant, right? We're taking the derivative with respect to lambda, so now we get 1 upon lambda due to the derivative of ln lambda times our constant xi. Does that make sense? Any questions? No? So we set all that equal to 0, and now we do some algebra and we solve. Okay. Well, if we take the sum of n many terms of minus 1, that's just 1 added to itself n many times. So that becomes minus n. That takes care of the sum, the summation of that first term here, minus 1. And then we have our sum for I goes from 1 to n of the second term. Now, this 1 upon lambda, that's a constant, so we can pull that out of the summation. We get this leading 1 upon lambda times our sum of all of the xi values. Those xi values are so-called captured under the summation. All of that equals to 0. So then we add minus n, we add n to both sides of the equation, we multiply both sides by lambda, then divide both sides by n, and we get an expression for lambda is 1 upon n times the sum of all of the measurements. And we'll call that lambda hat because that's the value of the statistic, a function over data, that we're going to use as our substitute. And that's the value of lambda where this product likelihood takes on its maximum value. And this expression we've been calling x bar. And so x bar is nothing more than the sample mean, which is also the so-called max likelihood estimate of the IID Poisson model. Does that make sense? So, of course, we know that now. We've been talking about the sample mean throughout the course of the semester, but the sample mean, until you prove it, you don't know really what the value is, the best value for fitting our models to data for the Poisson model. Does that make sense? Any questions? No? All right. And so lambda hat, our max likelihood estimator for the independent and identically distributed, or IID Poisson model, is just x bar. And it maximizes the likelihood function over all the observations. And we arrive upon that by setting the slope of this transformed likelihood function to 0 and solving for the parameter. Okay. And so this procedure is called the max likelihood estimation procedure, but the quantity lambda hat, our statistic, is called the max likelihood estimate, or lambda hat MLE. Okay, does that make sense? Any questions? And so when you're using APIs for fitting models to data, one of the options in the API is tell me the method for finding the estimator, or the method you use for fitting this model to data. And so it'll offer you, among others, max likelihood, method of moments, and there are a host of others that are less popular than MOM and MLE. Does that make sense? Any questions? No? All right. So at this level, if you never get into these optimization algorithms, I just want to make you aware that the method you use for fitting models to data is going to impact your results, but also your computation, because the MLE is more involved because you have to evaluate all of these likelihood functions. Okay. Any last questions? No? All right. Okay, so that's all I had for at least finishing up the segment on parameter estimation. And on Wednesday, we will use a number of these methods for various models. So let me bring up the other PowerPoint slide deck, if this thing will act as I hope it will. 21, save. Let's see where the other one is. Chug, chug, chug. I'll minimize that, let it do its thing. There we are, 23. Zoom, share screen, 23. And we'll go to slideshow. I forgot I had this. Forgot about the clicker. Slideshow. Hide meaning controls. Okay. All right. So now we'll jump into intro for machine learning. My area of research is machine learning, so this is always my favorite part of the course. Administratively, that hasn't changed. Please do take a look at the PDF I've posted to the course Canvas site. And so we talked about method of moments. And for each of these modeling techniques, it begins with you thinking hard and long about the model assumptions. And once you choose your modeling distribution, you look at the number of parameters that distribution has. And then you compute the first population moments, the first K population moments, and the first K sample moments, and then you equate them with one another and solve for the unknowns, which are the parameters of your modeling distribution. And so we also talked about just now max likelihood estimation. You think again long and hard about the problem, choose a modeling distribution, then you establish your likelihood function, make your monotonic transformations, set the derivative to 0 with respect to each parameter, and that solution gives you the statistic for the max likelihood estimate that's a reasonable replacement. And so for some distributions, method of moments might be better. For some distributions, max likelihood might be better. But I just want to keep you aware, when you're fitting models to distributions rather, to data, it's going to ask you, among other things, what method you want to use to do that fit. So anytime you're quote unquote fitting data to a probability distribution, it's employing some optimization method to try to solve for the parameters to use for the estimates for these unknown population parameters. Does that make sense? Any questions? No? All right. And so throughout human history, people, philosophers, sociologists, and computer scientists, neuroscientists have enterprised to try to unwrap or unpack what makes us think and how we think, what thinking and what learning really means. Now, has anyone heard of something called ChatGPT, right? These large language models? All those things are huge statistics engines that look at co-occurrences of words. Like if you said the yellow dog jumped over there are many choices for over the fence, over the bushes, over the cat, right? And if you give such a thing a lot of data, billions and billions of examples of valid text, when you give it a query or a prompt, it's going to pull up something that appears, and I'll use the word specifically appears to be contextually relevant. Now, does it really understand what you've told it? Not really. It's just really good at finding appropriate co-occurrences. And with ChatGPT, they don't just give you the best one, they give you the best one with a little bit of oscillation. And it's that little bit of oscillation that causes us humans to say, ah, this thing understands. It's very natural as a human being, because we're inherently social, it's very natural for us to want to ascribe human qualities to something that's artificial. But all it's really doing is memorizing statistics, a heck of a lot of them, over what word occurrences are. Now, certainly with ChatGPT, when you get a response from it, you engage in something called turn taking and you're correcting it. You're providing a little bit of a change to say, you know what, update your distribution over what word occurrences are for this particular utterance, and then it adjusts it over time. Now, this idea of adjusting over time when it is presented with new information, that new information wouldn't be jumps over the cat, it would be maybe jumps over the fence if you're talking about something that's a residential structure, for example. And so machine learning is the domain of the crafting of a certain class of algorithms. And these algorithms are purposed with adapting, adjusting their behavior based on the data that is input. When you provide these corrections to the prompts in something like ChatGPT and other language models, it's updating its distribution, that its statistic, that it's set of statistics that it's recorded about what are more frequent word occurrences. Now, in computer science, it's divided into three sub areas. Theory, which talks about rigorous methods for analyzing the resources, time, and storage and space consumed by computation. And then there's the systems area of computer science. That's about the study of the engineering artifacts. That's like your operating systems, that's your computer networking, and all the considerations and capabilities engendered by various choices within these engineering artifacts. And then there's the AI part of computer science, artificial intelligence, and that deals with the data, right? So data science is a part of artificial intelligence. Now, machine learning as a study, it sort of straddles, it's mostly in the AI side, but it does have a systems consideration. How do you scale these models? When you scale these models, how do you compute partial quantities, and how do you stitch those partial results to those computations together? There's also a theoretical side, something called computational learning theory, that talks about the physics of machine learning, all the interacting forces, and how you balance them in order to create an algorithm that quote unquote learns well. And we'll talk about a definition about what that means. And so machine learning kind of sits in the middle here, mostly as AI, but there's a theoretical analysis with machine learning as well as a systems component. Any questions? No? All right. And so there are various occurrences of what I like to call machine learning in the wild. And when you do a Google search, I'll direct your attention to that top row. There are three key ingredients in a machine learning model, even though the application might be dramatically different. And so it all starts with data in the case of a web search engine. And I remember when InfoSeek, the first statistical search engine, came out, it was a huge advancement over what was there previously, which was just basic term matching. And so in a Google search or a web search or a statistical search engine application, you start with your data, and that data is your set of web pages. And so your web pages have content, they have words, they have pictures, so-called semi-structured text or semi-structured documents. And then you have a model, your learning model, and this represents two things: a mathematical abstraction of your data, and then a set of algorithms that operate on that mathematical abstraction. And in the case of a web search, it's the so-called internet graph. A graph is a really important data structure in computer science, and it represents, in the case of the internet graph, the content of your web pages for these nodes or circles. And then these arrows or edges represent relationships. And in particular for the internet, it's hyperlinks. And so the operation on the internet graph for Google search. That's no secret anymore. Sergey Brin and Larry Page, you can read the original publication for something called the PageRank algorithm. And what that PageRank algorithm does, not only is it computing probabilities associated with word occurrences for nodes in your internet graph, it's also scaling that based on the distribution of inbound edges and outbound edges. Now, what is Google doing right now? You'd have to get on the PageRank team at Google and get a job there in order to find out. But the original PageRank algorithm, when they were PhD students at Stanford, you can find the publication, it's out there. Okay. And so at the end of the day, you have your application. And for a web search, it's a relevance rank list of pages. And so in the earliest days of Google searches, it would actually give you a ranked list of relevances. And that was the score associated with that scaled probability associated with documents. So this is the degree of belief that this particular page has content that matches what your query was. Does that make sense? Any questions? No? And then along the bottom, it's an entirely different app. Yes. Ah, it's based on two things. It's called diverse density. And so as you go from one part of the graph to another region of the graph, you look at how the in degree and out degree changes, you compute a distribution out of that, and you literally multiply that against the probability of the word occurrences. Now, the word occurrences, it's an enormous histogram, right? You can have a so-called dictionary, a set of word stems that can count in the hundreds of thousands, right? It's absolutely huge. And computing this would take a data center or many data centers, probably with about millions of different server instances. So it's a huge problem. And so they also have a distributed systems framework called MapReduce that facilitates that across a set of data centers. So to answer your question, there are various in graph learning algorithms. There are various algorithms that look at the change in degree and out degree as you go over regions of the graph, and they ascribe a notion of importance based on how dense your in degree and out degree is in regions of the graph. And then there's something called homophily, which is how similar that structure of in degree and out degree is as you go from parts of the graph to the other. And so in a internet graph algorithms book, there's some special monographs that talk about that, but diverse density and homophily and PageRank are standard graph algorithms that you can find that rescale. Where the secret sauce is all these extra decisions that they make, and I don't have any information about what Google does. Does that make sense? And so it's all sorts of graph operations. You can look for specialized pathologies in the graph structure. You can do things like diverse density. You can do things like homophily. How similar are they as you go across the graph? All sorts of things like that. To answer your question? Okay. Um, Along the bottom edge, we have a different application, self-driving cars, autonomous cars. And so here, our data, it's still data, but it's different. You have a bunch of sensors like video, allowing the automobile to see, so to speak. You have range sensors, you have LiDAR, you have radar. And then for our model, we have events. And these events represent constructs or patterns of occurrences between various things in these sensor streams that occur over time. Now, one example is something called lane keeping. And with lane keeping, you're using your video data. So it's about 60 pictures or frames per second. And you're computing gradients or slopes within that image. And you're extracting the lane lines and looking at your position relative to the center of the lane lines and making an automated decision to steer the automobile. Now, most of these things are so-called drive-by-wire. I know the Prius is drive-by-wire. Some of the other Toyota products, more modern vehicles are drive-by-wire. And when you have your gas pedal and your steering wheel, those aren't directly mechanically attached to the mechanism. There's a wire coming from them. It's just there to make you feel good. And it goes to the car computer, and it's the car computer that's actually giving the commands to the mechatronics that physically turn the wheel and change the acceleration. So that being the case, here we have a different type of data. Our model talks about temporal events detected in the sensor streams, and our application is lane keeping. And so, regardless of the type of data, the mathematical abstraction, time series, events in time series, and the application, we have these three things that are common. We have data, we have a model, which begins with a mathematical abstraction and an algorithm that operates on that abstraction. And then we have entirely different applications. But underlying this are these three components that are common regardless of the type of data and the application. Okay. Does that make sense? So let's take a look at what I like to call the anatomy of a learner. And in my own research, I deal with the physics of learning, how you change the way a learner or machine learning algorithm works in order to engender certain types of properties. And so we're going to frame it in an example for credit approval. Let's say, you're going to go to the bank and you want to apply for a mortgage. You go in and you apply for a loan, a mortgage, and they either accept or deny your application. So you come in to the bank, and there's this thing called an unknown target function. This is a theoretical construct, but it's important in framing the behaviors of the different components that comprise the anatomy of a learning algorithm, or I call a learner. And so this unknown target function, it's a function, and it's defined over big X, which is the set of information you'd get from the credit application. And for each piece of information, it's going to assign an outcome, either approval or denial, which is represented as the set I'm calling big Y. And so this credit approval function, it's out there merrily taking data from applications, assigning outcomes, approval or denial, but you don't have access to that. That's a recurring theme in statistics. But the good news is, while you don't know what this function is, it's out there working, and it's out there assigning approval or denial outcomes on credit information for many, many, many people over time. And so you have access not to this function. If you knew the form of the function, just code up the function and you're done. But you don't know what this function is, but it's telling you through the historical records, the so-called training examples, what it would do for certain types of credit. Okay. And so floating out there also given to you are your historical records. It's called sometimes a label instance pair. And for each credit application data are X's, you have a corresponding Y. This person was accepted. This person was denied credit. Does that make sense? Okay. We also have something called a hypothesis set. This is where your educated guess, your mathematical model, your mathematical representation comes in. You study the problem and you make a good guess about what the right representation might be. Now, sometimes this is very generous and it's very broad. Sometimes it's less generous and you make this very specific. And these would be candidate formulas that you kind of believe that might include what you know about the problem, that might include the functional form for this unknown target function. Okay, so there's some educated guessing coming in here. So then we also have your learning algorithm. Now, your learning algorithm inputs two things. It inputs all of your historical data, your label instance pairs, those examples from the unknown target function about how it would associate an outcome for the credit approval problem. And it also inputs your family of functions, your educated guess, your hypothesis set. Now, it's the goal of the learning algorithm to search through your family of functions, your hypothesis set, and it tests each function that it encounters when it searches through your hypothesis set. It tests it to see how well it does relative to the ground truth from these training examples over the historical data. So it inputs each one of these X's, and then it computes an approval or denial, and then says, okay, how did I do? How did I compare to what's known historically, the decisions, labels assigned by this unknown target function? Does that make sense? Any questions? No? All right. And so you do this, you run this algorithm, And certainly you have concerns about time and space, but in machine learning, one of the physics you're concerned about is the impact of the size of the vector. It's a random vector, how many positions you have in this random vectors or the dimensionality, but you're also concerned about how much data you have. Now, your algorithm churns over some number of steps, and then eventually it halts, it finishes, and it outputs something called the final best hypothesis. It's that function from your hypothesis set that most closely mimics the labeling action of this unknown target function. But it measures this idea of most closely mimics by computing how does it compare with these y's assigned by this unknown target function. Does that make sense? Any questions? No? All right. And so I've colored some of these boxes. Some are in red and some are in black. Yes. It doesn't accurately, based on the training examples, it says this is the best performer selected from this hypothesis because you don't know yet. And what you asked is very important. There are some rigorous methods that talk about the balance you strike with these different parts of the anatomy in order to ensure that a certain type of best solution is going to apply well to new examples that you haven't seen yet. And that's called generalization error. And so it's kind of a tough question to answer without getting into some of the theory, but at this juncture, at this level for this class, it's not the best, it's the best that it knows given the existing data. Does that make sense? So it's trying to mimic the unknown target function based on what it knows from the training. And that's the best it can do. Okay. Any other questions? No? All right. And so the red boxes, you don't have control over. You have no control over what the real function is out there that is assigning approval, denial decisions to credit application data. You have no control over that. The training examples, you have no control. If you're a bank, you have no control over people in history who have come into the bank. You have no control. They're just there. They're given to you, right? But everything drawn in black, the learning algorithm, hypothesis set, and because of the action of the learning algorithm, it searches and arrives upon a final best hypothesis. You have control over everything in the black shapes. Does that make sense? All right. And so in machine learning, the combination of the mathematical family of functions and the learning algorithm that acts in searching through those functions for the best one, those are called your learning model, right? So when you talk about a machine learning model, the first thing you should ask is, what is my family of functions? And what is my algorithm that searches through that family of functions for the final best hypothesis? Does that make sense? Any questions? And so, but wait, there's more, right? Now, how does, and that addresses some of your question, how does your learning algorithm know what is the best, right? Final best hypothesis. You measure that, and that's your error measure. Sometimes it's called a loss function, right? In learning from data, it's called in-sample error. It's the error or the difference between the ground truth labels, the Y values on the historical data, and the predicted labels by your current working hypothesis. Whatever that difference is, it's on the points that you have in your sample, or so-called in-sample error. And so the idea then is, how do you find a final best hypothesis by balancing the right trade-offs in your anatomy such that when you have a good enough in-sample error, it's going to perform well using that final best hypothesis on brand new data that's not from your training examples. Does that make sense? Any questions? No? All right. So you need an error measure, and there are various considerations about how you measure error, so-called type 1 and type 2 error, whether it's a false positive or false negative. And there are lots of considerations about what is the expense of an error. If you're doing, for example, biometric identification from fingerprints, if you're trying to grant or deny access to sensitive material, well, you're going to set your error function that a false positive is more expensive, right? And so you can absolutely control this error measure because that's also going to encourage which regions of this hypothesis set make better functions. Does that make sense? Any questions? All right. So now we also have another component that I haven't talked about, and that you don't have control over, and that's a probability distribution. It's a joint probability defining random vector instantiations, and it's this probability that's responsible for giving you your training examples. This defines that Joe Smith, who had a certain credit profile, walked into your store, or Jane, I'm just making up names, Jane Smith, Jane Smith, it's original, also walked into your bank and filled out a credit application. All right. And so this probability distribution that is giving you these training examples, the vector instantiations, also is the same distribution you should have no control over, that's giving you this edge, and these are the so-called out of sample points. So let's say you have a camera set up on Main Street and you're looking at pedestrians as they're walking towards the campus, and you're doing some face detection. There's some privacy issues with that, and you're recognizing students by comparing their faces to the student ID database. And when you get on campus, this jumbotron says, "Hey, good morning," and says your name, right? That'd be kind of creepy, but it's certainly an application. And so with this, you would have your historical data, this edge going from your distribution to your training examples, that's giving you the student ID database data. And then the out of sample data, those are the measurements of the camera in the wild as you're crossing the street. Now, in many cases, most cases, ideally, this distribution that gives you the historical data should also be the same distribution that gives you the new data out of sample. But that's not always the case. And there are certain things called transfer learning where you can exploit overlap in the distribution that gives you training examples to a different version that gives you your out of sample data in the wild. Does that make sense? Any questions? So we could spend 2 semesters on machine learning, and I hope I get to teach my version of machine learning and pattern recognition. Pattern recognition is the algorithmic implementation of various components of the anatomy, and the machine learning talks about the physics between the components. Okay, so here's some examples of learning models, and I'm just going to mention their name. A neural network. If you've ever heard of deep networks are just neural networks that have many layers. And a neural network is nothing more than a special category of functions. These functions are weighted sums of inputs, and you take that weighted sum of an input and you send it through a nonlinear function. Each one of those outputs are then aggregated as weighted sum to another set of aggregators. And so that's a type of compositional function, weighted sum through nonlinearity, through weighted sum, through nonlinearity, again and again and again and again. That's a special class of functions, a type of hypothesis set. Now, the algorithm is called backpropagation. It's an implementation in a clever way. Oops. What's my mother calling me? I thought I had do not disturb. I'm going to call her after this. Just lost my thought. Yes, all right. So backpropagation is a clever way of implementing partial derivatives. And it says if the output of our current best working hypothesis is different from the ground truth, then you change these weights among these weighted sums using a clever way of computing the partial derivative. And so here, the neural network is a class of functions, a family of functions, a hypothesis set, and backpropagation is the algorithm that you use for searching through it. Any questions? I'm not going to explain all of them. So regression is a type of linear model. Least squared projection, matrix inversion, is how you arrive upon this final best hypothesis, which gives you your regression weights. Decision trees, which we'll talk about in this class, is a type of interpretable model. You can kind of read off the result of it. And gain ratio splitting, which uses entropy, is the algorithm for how you make the choices about building this decision tree. A Gaussian mixture model, Gaussian distribution is a normal distribution, and it's a way of fitting models to data that have many that are composed of a set of normals. So for example, in the homeless population example, if you have ages that you're trying to model, age represents time, that's well modeled by a normal or Gaussian distribution, you might decide there are four groups: veterans, aged out foster children, etc. And you might decide each of those groups has an age variable that is different. So how do you fit four age groups to a population? That's called the Gaussian mixture model. And that's a family of functions. Probabilities are functions. A mixture of probabilities is another type of function. So that's a hypothesis set. And expectation maximization is the algorithm for how you find those parameters of that multimodal Gaussian. And then lastly, Markov chain Monte Carlo is a way how you approximate a distribution. It's a graph-based method, and Metropolis Hastings is the algorithm for how you train that model. So in any case, any machine learning approach, it always has some hypothesis set or family of functions or models and an algorithm that operates to try to find the parameters of that model that best mimic this historical data labeled by the unknown target function. Does that make sense? Okay. And so a simple example, and we have about 7 minutes left, is the credit approval example. And we'll end with this. Imagine your bank and you want to build a system that's going to decide, based on information culled from credit applications, whether or not the applicant, represented by their vector of measurements, is going to be approved or denied for the loan. So you go online, it used to be you go into the bank and you fill out an application and they ask you all sorts of things. Why certain things, I have no idea. And then you input it into the credit approval system, and it's an automated system. It's a learner, and it spits out, based on that vector instantiation, whether someone's approved for the loan or denied the loan. Now, with any machine learning approach, it's really important to consider the ethical parts of this. Now, I'll ask you, why do you think it would be a good idea to automate credit approval? And why do you think it might be a bad idea to automate credit approval? So who thinks it's a good idea? Nobody thinks it's a good idea to automate it? Yeah, good idea. Why do you think it's a good idea? Okay, okay. hmm hmm Okay, yes, that's a great answer. You can choose things and design your system to reduce or eliminate bias. Okay. The other part is why it's a good idea. It's federal law that if you're denied credit, you can request an explanation in writing why you were denied credit, and they have to furnish it to you. And so if it's an automated system, now you can record what the decision was for the automated system. This attribute was below this spec. That attribute was above that spec. Now, certainly you could go to court and argue about whether those attribute levels are appropriate based on the law, but at least you can furnish a reason why. And that reason is less so due to human error, but it's really important to look at the data that you're inputting. So why do you think it might be a bad idea? Anyone want to guess why it might be a bad idea? Why do you think it'd be a bad idea? Yes. Mhm. Yes, it's only as good as the data you input. And I'll add, these don't make judgment calls. You might have, say, a family that's lived in the same area for 100 years, a couple of generations. And even though they don't look like good credit risks on paper, they're known to always meet their loans. And so because there's no qualitative segment to this, it's just going to make that decision regardless of how close to that cut point that it is, right? And so in practice, whenever you have an important decision, you defer to the automated solution when the decision is more obvious. But if it's one of these kind of close calls, practice is to have it set aside that record and have a human being look at it, right? And that's for a whole host of types of application domains. You don't let the system make the decision. It's a recommendation, and then you have somebody review it, especially in those cases where someone was very close to the line or qualitatively there's a different story. Does that make sense? And that's both in the choice you make for how you measure error, as well as when you deploy this thing on new data and it's helping you with these decisions. It's an assistant, not a replacement. Okay. And so let me squeeze in the next 3 minutes. In a learning system, we start with data, and that data is represented as vector instantiations. And you can certainly plot those vector instantiations as points on some highly multidimensional space. So in this case, we have 2 dimensions. Along the horizontal axis, we have salary, and that's one of the questions they ask in a mortgage application. And on the vertical axis, they have years in your current residence, be that apartment or you own a home already. And so some of the ideas why salary, well, the idea is that depending on your salary, it increases your ability to pay off the mortgage note, and that makes you a better credit risk. In terms of years in residence, you're not just going to take the money and run, right? You're actually going to stick around because you've been around a lot. And the idea of someone who's been in an area longer is that person is more stable and therefore a good credit risk. Now, certainly, I'm not going to argue about the merits of why these are 2 of the many factors that are measured, but certainly they are included at the moment in mortgage applications. And so we start out each individual from his or her mortgage application, imagining their salary and years in residence are written down, and we can register each one of those vector instantiations as a point. Okay, so we might have somebody who's 70K, 7.5 years, 55K, 10 years, maybe 75K, 15 years, and so forth. So each one of these vector instantiations represents an individual, not by name, but by the information culled from their mortgage application. And so when we have this, okay, if we can have 3 points, we can have an arbitrary number of n many applicants from your historical data. And so if we take our data set, one of the observations that you'll see is we get what are called a point cloud in feature space. Another observation is to look at the relative relationship or the so-called geometry of the point cloud in feature space. Now, in this particular case, you'll notice that I can almost kind of see a line that could separate the green labeled points from the red labeled points. And these labelings are depicted or are depicting a coloring of the historical data. Those points that are green were those from historical records that were approved for mortgage. And those in the red are historical records, applicants who were denied a mortgage. Does that make sense? And so now what we enterprise to do is to find a family of functions that best mimics this coloring of our point clouds in feature space. What kind of function? Okay, well, that depends on the geometry of your point clouds in so-called feature space. And it's called feature space because the values of each one of these vectors is called a feature. We have the salary feature, the years in residence feature, and space is Cartesian space, the representation of vector instances in multiple dimensions. I'm kind of thinking ahead on something else. And so here we have point clouds and feature space, and the family of functions for our hypothesis set are going to be informed by what you understand about the geometry. And so to continue this, we'll stay tuned for Monday. We'll pick back up then on what you do with these point clouds in feature space. So we will end there. Have a great weekend. Get out, get some sunshine. And I'm going to call my mother, see what it is she wanted. I block all my calls except for my mother. All right. I'll see you on Monday.